Bazarko. I am the president of the Philadelphia chapter of the Shevchenko Scientific Society. I welcome all of you here for the next in a series of learned lectures, which is different today because it's in the physical sciences as opposed to the humanities. I am sure that you'll find the lecture interesting, informative, and phenomenal. I will ask Magister Mazurkiewicz, the chair of the program committee of the Shevchenko Society Philadelphia chapter, to introduce the speaker. Proszę Pani Magister.
Тоні, дякую. Так, добрий день і слава Україні! The last few days, some of us had the unique opportunity to see the eclipse, albeit only on television. Today, we have the unique opportunity to delve into the cosmic universe. I am honored to introduce our brilliant speaker, Dr. Andrew Bazarko. Andrew Bazarko trained as an experimental particle physicist. After earning his PhD at Columbia University, he was a staff member at CERN, the European Laboratory for Particle Physics in Geneva, Switzerland, and later became a faculty member in the physics department at Princeton University. During his academic career in particle physics, he worked on experiments at several of the world's largest particle accelerators. He spent over a decade working in industry, designing, manufacturing, and modeling the use of instruments that employ the technology and techniques of nuclear physics for geological characterization. He was issued a patent and became increasingly involved in scientific project management. In 2016, he became Simons Observatory project manager and returned to Princeton University. The Simons Observatory is a new facility being installed in the Atacama Desert of northern Chile. To look to the sky and measure the cosmic microwave background. The project is a collaboration of several of the world's leading universities. In his talk, Dr. Bazarko will explain what the cosmic microwave is and will also provide the context for the questions the Simons Observatory aims to address. After his brilliant presentation, Andrew Bazarko will entertain questions from our guests. Dr. Bazarko, please.
All right, thank you very much. Well, I'm very happy to accept this invitation from the, Shevchenko Scientific Society. My parents very involved, so that there's a relationship here between someone who already spoke, and so thank you all for coming. So let me put this in presentation mode and tell you that. Right, so I'm working on the Simons Observatory. You can see it's a collaboration of many institutions. And so I'll have a little bit more to say about that, but the outline of my talk is really to give you an introduction to cosmology and then conclude with saying something specifically about the Simons Observatory. So, as I'll talk about several topics: distances in the universe, the observable universe, the cosmological principle, the fact that the universe is expanding, the age of the universe, how telescopes let us look back in time, and telescopes are essentially time machines. Dark matter and dark energy, which are kind of, mysterious things you may have heard of. I'll describe what that is. I'll get to the cosmic microwave background, which you've already heard mentioned, so I want to make sure you hear that term mentioned, the cosmic microwave background, and then conclude about my specific project. Let me just reference this book, written by a colleague, faculty member at Princeton. That is good. Everybody can see the screen. And also someone who's working on the Simons Observatory, Lyman Page. So just by way of introduction, I want to say it's remarkable, in a sense, how simple the universe is, how on the largest scale we understand so much about the universe. And that understanding is contained in something called the Standard Model of Cosmology. Now, when scientists use the word model or theory, you might say, oh, that's just a hunch, just a theory. Well, no. A scientific theory, is actually an entire mathematical framework that can make predictions, is testable, can be falsified. And so what we have in the Standard Model of Cosmology is that, a very good understanding of the universe. And a great deal of that knowledge, as I hope you'll see, comes from measurements of the cosmic microwave background. And so, of course, the study of cosmology deals with kind of those most basic questions, that question of in the beginning. And so cosmology is that scientific quest to understand maybe that kind of very most basic question. All right, so distances in the universe. Let's start with that. So we're going to use light to measure distance. Light travels at a finite speed. So, for example, light coming from the sun takes 8 minutes to reach us. So when we look at the sun, we're actually seeing it as it was 8 minutes ago. So we're going to consider the time it takes for light to travel a year. That distance is a light year. And so here the Earth, are part of the Milky Way galaxy. The Milky Way is our galaxy. We can't go out to actually take a picture of our own galaxy. But here's another picture of a different galaxy, which is thought to be basically a twin of the Milky Way. It's a spiral galaxy. And the Earth, our solar system, is on the arm of the spiral galaxy. The Milky Way galaxy contains 100 billion stars. And that's a big number, but, for comparison, 100 billion is also the number of neurons in the brain. And the diameter of the Milky Way is 100,000 light years. Okay, so that's one dimension. Now, our galaxy is part of the local group of galaxies. So another dimension of the local group is 6 million light years across. And so within the Milky Way, there are, what does it say here, about 50 other galaxies. The Milky Way is one of the bigger ones, but it's not the biggest. Andromeda is a bigger galaxy in our local group. The distances here between the galaxies are large, but we're still talking local. So what's the difference between local and cosmological? There's not a firm boundary, but consider a cosmological difference to be 25 million light years. So, the local group is just a tiny fraction of this cosmological volume, right? So if you think about volumes, our local group is about 1% of this sort of bigger thing I'm describing, this 25 million light year cosmological distance. All right, so the observable universe, what can we see? So this is an amazing image. It comes from the Hubble Space Telescope, which is a telescope that was launched in orbit around the Earth. And this picture is what's called the Hubble Ultra Deep Field, which is basically a very long exposure into a tiny patch of the sky. So it covers an area 1/60th of a full moon. So just train the camera, do a long exposure for about 300 hours looking at this tiny patch in the sky. And the amazing thing about this image is it's mostly galaxies you're seeing, not individual stars. And I'll state that many of these things are billions of light years away. So you can count the number of galaxies in this image. What you count is about 10,000 galaxies. So scaling that to the entire sky, about 100 billion galaxies. So it's a big number, but it's a finite number. And so with this image, we a couple profound ideas. That, first of all, we're looking really hard, and this is what we see. This is what's observable. And secondly, there's a finite number of galaxies in what we can observe. All right, so now I want to introduce this thing called the cosmological principle. So imagine now, put aside the finite speed of light. Imagine that you could travel, anywhere in the universe. So imagine there's a colleague of yours 10 billion light years away, and you ask that colleague, tell me what you see. And that colleague describes his local group, and you compare it to your notes about your local group, and the idea is these two descriptions are going to look the same. Right? So this is the cosmological principle. It's basically an extension of the Copernican principle, right? We're not special. Our part of the universe is like any other part of the universe. So in broad strokes, every place in the universe looks similar, and the same laws of physics apply. All right? So another way to state this is the universe is homogeneous and isotropic. Homogeneous means it looks the same at any point. Isotropic, it looks the same in any direction. So we've already talked about this 25 million light year cosmological distance. Basically think of any 25 million light year piece of the universe over here looks like another 25 million light year piece of the universe over here. All right? So this is the way we need to consider the universe. So yes, what we're used to seeing is things are different. When we look at the sky, things are very much, not isotropic necessarily, but on big enough scales, the universe is homogeneous and isotropic. All right, so up to this point, we've described the universe as basically static. Now let's bring in another piece, that the universe is expanding. So actually, so I've already mentioned the Hubble Space Telescope was named after this astronomer, Edwin Hubble, who worked about 100 years ago. And about 100 years ago, before his discoveries, the Milky Way was it. People thought the Milky Way, this is our universe. There were stars. There were wispier things called nebulae, which were considered to be part of the Milky Way. And one of the transformations Hubble made was to point out that, no, there are galaxies that exist outside of the Milky Way. Right? When he first came out with these observations, this was resisted. And then later, he continued to study galaxies and noted that the galaxies are moving away from us. So a little bit more about that. So actually, it built on several things going on in astronomy. So earlier in the 20th century, another astronomer, Slipher, working in Arizona, pioneered the use of the Doppler effect in measuring the velocities of objects in the sky. So just like, a police officer measures you driving down the highway, cars moving away from you, their frequency goes down. I don't know how to, right? You can look with light, and if things are receding from you, there'll be the same thing. There'll be a Doppler effect, and the light will be redshifted. It will be shifted to frequencies that are lower. So this was pioneered. He was looking at nebulae, and he noticed that nebulae were redshifted, meaning they're moving away. So there was that, that was in the early 20th century. Hubble's observations were, these nebulae are actually galaxies that are moving away. Einstein had already come out with his theory of general relativity. And Lemaitre, a Catholic priest, astrophysicist in Belgium, applied general relativity, knew something about these redshift measurements of nebulae, and was the first to propose. He said, okay, applying general relativity, the universe will be expanding, and that probably explains why these nebulae are redshifted. And then 1929, Hubble systematically observes galaxies. How do you do that? I mentioned redshift is how you measure velocity. How do you know how far away they are? You need something called standard candles. So something in the sky, its intrinsic brightness, and then you observe it. How bright is it to you? that tells you how far away it is. You know its intrinsic brightness, you see how it is. So there are these stars called Cepheid stars that are standard candles, and using that, he came up with a velocity-distance relationship. When you look out into the sky, things are further away, they're moving faster. So this is the very simple relationship that the velocity is proportional to distance, and the constant of proportionality, denoted by that h naught, that's been named after Hubble, that's the Hubble constant. And so approximately for every million light years further away something is, it's moving away by 15 miles per second faster. All right? So, you stop and think about that. So I look in that direction, everything's moving away from me. I look in that direction, everything's moving away from me. Sounds like I'm in the middle. I'm in a special place, right? So are we in the center of the universe, right? So you're standing here, we look that way, you see the galaxy, and you see them, these are moving at a certain velocity, the ones that are further away are moving faster. So think about this. No, we're not in any special place, because if you consider moving to that, then when you look to your right, you'll still see things moving the same way. You look to your left, you still see things moving that way. And so because of this, all observers anywhere in the universe see the same thing. It only appears, apparently, that you're in the center of this expansion. Right? So the important thing to note is the Big Bang is not a standard explosion. Right? In the standard explosion, things would go out and everything would have the same speed, right? You get the initial velocity, and so, you had your cannon in space exploding. Every one of these balls, if you measured its speed, you would expect it to be the same. That's not what the galaxies are doing. So, how to think about the galaxies receding this way? And the radically, perhaps thing to think about, don't think about the galaxies as moving away in a fixed space. Consider space itself to be expanding. All right? So, here's an example. So, you look at one time and you see the galaxies. This galaxy is a distance d from you. The other galaxy is twice as far away, 2d. And now in a time interval going to the next time, what you do is you make space. So this space, we double it. Right? So this space you've doubled, and the next space you've also doubled. So now in this time interval, this one is 2d away, this one is 4d away. So you just work it out. So what's the apparent velocity you see? Well, in that time interval, the first galaxy has moved by speed v1. The second one has moved by speed 2v1. And so by doing this, by thinking about I'm expanding space, you see this velocity, apparent velocity of the galaxies moving away. So this is an example in one dimension. You do an analogy in 2 dimensions. You think of being on a rubber sheet, and pulling it, and everything is expanding away from itself. In 3 dimensions, maybe think of a grid of these kind of tinker toys, and what's happening is the rods between the hubs are expanding. So, so it's expanding in 3 dimensions, and everything is moving apart. Right? So that's the way to think about it. So what's happening, the galaxies are moving away from us because space itself is expanding. Don't think of the Big Bang as a exploding bomb. It's this different thing. And so you think about it that way. So where did the Big Bang happen? It happened everywhere. Space is expanding. So, if you're standing here, you see everything expand. If you're on this other galaxy, you see it. It's happening. It happened everywhere. Right? And so we think of the Big Bang as this explosion of space. It's where we start our clocks, in that sense. Right? And so with that, we get to, the age of the universe. And so the Big Bang, if that's where we start our clocks, and that defines a finite age of the universe. So the galaxies are moving away, so in the future they'll be further away. So that means in the past they were closer together. So we use a term called compactness. So in the past, the universe was more compact. When the universe was twice as compact, it's a linear distance. Everything was half the distance from where it is now. So when the universe was more compact, things were getting closer and closer together. And so you extrapolate this back in your head. You keep think back in the past, closer, closer, closer. At some point, everything was on top of each other. That's t equals 0, the initial time. So we extrapolate back. The important point is what you can extrapolate back, and you extrapolate back in a finite amount of time. That's the age of the universe. So how do you determine that? Well, extrapolating back, velocity is just distance divided by time. We already have an expression with the Hubble expression, how velocity relates to distance. So you just plug that in, very simple. And 1 over the expansion is this Hubble time, and that would be your first order approximation of what the age of the universe is. And so, here I just, that number I gave you before, this is the, in slightly different units. So 70 kilometers per second per megaparsec. So mega meaning a million, and a parsec is 3.26 light years. So anyway, this is just the common units that people use. But literally, you just take 1 over that number. You could do it yourself, and you'll get 14 billion years. So that's the age of the universe. I point out that this very simple calculation assumes that this Hubble expansion is constant throughout time. In fact, general relativity says there'll be slight nuances depending on the composition. So taking those nuances into account, the accepted value of the age of the universe is 13.8 billion years. And the accepted uncertainty on that is about plus or minus 0.2 billion years. That's where we stand. Okay? So coming back to our Tinker Toy analogy, you've got the hubs. They're getting smaller, 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 and 13.8 billion years, somehow they were all on top of each other, smushed together, right? That's the picture we have. Now, to the extent that these Tinker Toys are infinite today, you're scrunching them back, you're making everything much more compact, but if they were infinite today, they were infinite, they stay infinite going back in time. So that's the picture we have. Maybe say an infinite grid of these Tinker Toys. They got much more compact, but still infinite back at t equals 0. It's hard, maybe hard to fathom, but that's the picture. So we come back to the observable universe. Now we really understand what that is. So the age of the universe is finite. All observers agree about its value. So because the speed of light is finite, all we can see is light that had a chance to travel 13.8 billion years. Any light that has to travel longer than that can't reach us. We can't see it. So the observable universe is, think about a sphere that extends out 13.8 billion years in radius, and anything beyond that is not accessible to us because light can't reach us. Now, another thing to just think about is that surface that emitted that light, that's been taking 13.8 billion years to reach us, continues to expand. So when that light reaches us, that surface now is actually 46 billion light years away. But nothing older than 13.8 billion years can reach us. And I say when cosmologists talk about the universe, they usually talk about the observable universe. But if you just do a thought experiment, if you were 13.8 billion light years away, you would be sitting and you would see something very similar. It would just be centered in a different place, and you would see a different 13.8 billion light year sphere around you. So, we already sort of mentioned this. Is the universe infinite in space? Well, we don't really know, but as far as we can tell, yes. The observations tell us that an infinite universe with properties similar to the cosmic environment around us is the best and simplest description of the data. We can't tell the difference between having some kind of edge. As far as we know, it's infinite. We can only see 13.8 billion light years away. So the picture to have is that the universe is like a big container of chocolate chip ice cream. A huge container of chocolate chip ice cream. A scoop would be our observable universe. So I say, okay, the chocolate chip ice cream, the galaxies are the chocolate chips, the ice cream is the space, right? Consider this big tub of chocolate chip ice cream. You take out a scoop from somewhere in the middle of that tub, away from the edges. That's our observable universe. You could take out another scoop somewhere else. That could be another observable universe, but they're the same, you know. And as long as you stay away from the edges, right, no problem. If there are edges, we don't know. They would be something new, some kind of new physics, something not accessible to us at the moment. But that's kind of the picture to have. All right, so telescopes as time machines. So coming back to this image from the Hubble Space Telescope, and again, when we see the sun, we see it as it was 8 minutes ago. If we see an object that's 20 million light years away, we're seeing it as it was 20 million years ago. Right? So here's an analogy, you know, sitting in this room, auditorium, you guys are galaxies. I've got my telescope. I look out, and in the front row, I see all of the oldest among you, say the 50-year-olds. And then in the next row, somehow all the 40-year-olds sat down. And in the next row, it's all the 30-year-olds. And in the next row, you know, the 20-year-olds. And as I get to the back, you know, there's a row of all infants. And in the last row, it's empty. For some reason, no one's, and then the back wall is glowing. Okay? And furthermore, the people in the front, everybody's blushing, but the people in the front just a little bit, the people a little bit more, and then the people in the back are you know, the infants are really just bright red. So what's going on? So the reason everybody sat down, ordered themselves by age, is because that I'm basically looking back at time. So the galaxies that have had time to be close to me have had time to evolve. They're the most mature. As I look further and further away, there hasn't been as much time. Those are the immature galaxies. I go all the way to the back where there was no one. Well, there hasn't even been time for the galaxies to form. And then, so there's that. Why is everyone red? Well, it's because of this Doppler effect, this redshift. So the people in the front are moving away less slowly, so it's just a light pink. But the people in the back are moving away much faster because there's more distance. So they're much more redshifted. That explains that. Okay? And then what about this glow in the back? What's that? So the universe was much more compact going back in time. So that means the energy densities were much higher. And so galaxies need time to form, so they cool, they form, so that's why the mature galaxies are later in time. The immature galaxies haven't had time to form, they're back in time. And you go further back in time, there hasn't even been time for the galaxies to form, it's just gas. You know, so this area here, you labeled dark ages, just gas. And then, more and more energy. So what happens? You have ice, it melts, it becomes liquid. You have liquid, it gets hotter, it becomes a gas. The gas gets hotter, what does it become? What's this phase of matter that's even hotter than someone said it?
Super hot.
A plasma. Right? So a plasma, that's when you've got the electrons are torn off of the atoms. And so now you get to a point where this plasma becomes opaque. And so the glow we're seeing is this hot plasma from the birth of the universe that now is like a plasma screen that surrounds us everywhere toward the edge of the observable universe. Because we're looking back in time to things that happened, that far back in time. Right? So now I've just introduced this cosmic microwave background. So it's this opaque radiation that's coming to us from all around when we look. Okay, so that's, we told you you'd hear about the CMB, so now we've just introduced it. All right, so I want to introduce a couple other concepts that are, kind of exciting, mysterious: dark matter and dark energy. They're two important contributions to the universe that you may have heard of. So dark matter. So a simple example is you go out looking at a star, and you notice a star that's moving in a circular path. And so what you would immediately conclude is that there must be some kind of mass that it's orbiting, right? Because the only force it has is gravity. So there must be a mass, but you just don't see it. So you start looking for this missing mass, this missing matter. Your first thing would say, well, there must be a dim star there that it's this orbiting around. But then what happens if you can't find it? So in fact, over many decades, astronomers have been looking for missing matter. And by looking at clusters of galaxies at first in the 1930s, seeing that the clusters of galaxies are rotating and there's matter missing to explain how fast they're rotating, and then more observations of individual galaxies, looking at the spirals of galaxies, looking at how fast those spirals are moving, considering how much luminous matter there is in the middle, and coming to a conclusion that just seems like we can't find matter to explain this gravitational attraction. And in fact, as I'll briefly show you toward the end, the cosmic microwave background provides even more evidence that there's missing matter. And so the conclusion is that, remarkably, there's a lot of missing matter. And the effects of this missing matter are not subtle. And in fact, the best accounting is that in the universe, there's 5 times more dark matter than there is ordinary matter. So, wow, that's, one big conclusion. So just to recap, so what is, dark matter versus ordinary matter? So matter is any substance that has mass and occupies space. Ordinary matter is kind of the things we know, things made out of protons, neutrons, electrons, things we can see, right, with our eyes or with our telescopes, things that react with the electromagnetic force. Dark matter has mass and occupies space, but it doesn't reflect, absorb, or radiate light. So it's something different. What is it? We don't know. You think we find some kind of particle ultimately that may explain it, but we're still looking for it. We infer its presence by gravity. In our everyday life, it has no bearing. But there are laboratory experiments now underway to try to detect dark matter. And so maybe if you heard of these weakly interacting massive particles, cleverly called WIMPs. So there are experiments out there, trying to find them in the laboratory, because the notion is that they must just be floating around, but they just don't interact. So can we build an experiment in a laboratory that's sensitive enough that will happen to catch one of these interactions? Okay, so now dark energy. So dark energy is explained because further observations of the universe find that not only is the universe expanding, but this expansion is accelerating. And so it was only in the late 90s that these observations were made that show that the expansion is accelerating. And so Hubble's discoveries were made with standard candle stars called Cepheid stars. They needed other standard candles to measure things further out. And so those standard candles are a particular type of supernova explosion. And so the particular kind of supernova explosion is labeled a type 1A supernova explosion. It's made when a white dwarf star accretes mass. That mass gets beyond a certain critical mass. When that happens, boom, there's an explosion. And because it's a certain critical mass that's so well defined, these explosions are thought to be very, very characteristic, very standard. So you can use them. You know how much energy is released. And luckily it's a big explosion, but it doesn't just happen in an instant. It's actually for a month. This supernova shines like several billion times as the sun, several billion times as bright as the sun. So you can, telescopes look at the sky, they don't see anything, and then all of a sudden, they see something, and they can measure those supernova explosions. And so it allows them to find these standard candles much further away from us. And what was observed is that they're dimmer than they would be expected to be, given how fast they're receding. So it's showing that as you look at things further out, the Hubble expansion is a little faster than it is closer in. So the universe is accelerating in its expansion. So, just to say that, an example. So we said that the Hubble expansion is 15 miles per second per million light years. So something 10 million light years away is moving away at 150 miles per second. And so what these observations show that as time goes on, that's going to change and it's going to move away even faster. So this kind of has implications because it says not only are things receding from us, but they're receding from us at an ever-accelerating pace. So it just means that, in a sense, the observable universe is going to keep on receding and getting it effectively smaller as time goes on. I know, it'll be billions of years, but it's, something to fathom. So what does it mean that we see that the universe is accelerating in its expansion? Well, it means that space itself has a pressure that's causing things to accelerate. There has to be a force that's causing the acceleration, and that means space itself has this property that it accelerates itself. And so actually, when Einstein was developing general relativity, in the equations, he thought, I can add a term that is this kind of pressure. In his equations, he used the Greek letter lambda, and he called it the cosmological constant. And he introduced it because he said, I'd like to see a universe that's static, and gravity would tend to make things collapse. So I'm going to add a little fudge factor that's going to be a little bit of pressure that keeps things pushed out. And in the end, he thought, that's not very elegant. Can't be right. But it turns out, yes, it is. And in fact, it's an even bigger contribution than he first, proposed. So right now, this looks like to be the simplest thing. There's this constant pressure of space itself. It contributes to this dark energy, and it causes the universe to accelerate in its expansion. So this, of course, is a very deep concept. It's not part of anything else in physics. We can't think of any laboratory experiments that would test this. And why is it there at the moment? We don't know, but we observe that it's there. Okay. So the cosmic microwave background. So finally, we'll get to that. So I'll explain to you why I have it in this sort of dappled colors here. But it's, as we said, it's that glow in the back of the black of the room. It's something that's coming to us from the edge of the observable universe. So it was discovered ultimately in 1964 in New Jersey at Bell Labs, where they were doing work on satellite communication with microwaves. This is actually the receiver they were using. It still exists, kind of as you can go see it in New Jersey, and they'd been hearing this hum. That as much as they tried to eliminate all the noise, there kept to being this hum, and it was actually Penzias and Wilson who were assigned, track down the noise, figure out what the noise is. And so they looked for many, many things. And, the cute thing that's always gets mentioned is they thought, maybe it's dirty inside because pigeons fly inside and leave their droppings. And so they climbed around inside, to really clean it out, couldn't get rid of this hum. And they finally, started to conclude, maybe it's real. And, maybe, and they looked around and they could conclude if it's real, it's not coming from any source in the galaxy, it's coming from outside. And they knew that there were other physicists at Princeton who are actually gearing up to do their own experiment to look for this. And so they communicated with them and said, we're getting this thing. We really think that this what this might be. And, the physicists at Princeton came back and said, yeah, we think you've got it. You found the cosmic microwave background that we've been thinking about. And so, just to mention that, Penzias and Wilson won their prize, and James Peebles, who is still around, has been one of the key players in the theory of cosmology. He also won a Nobel Prize, just very recently for all his work. So that's the discovery of the cosmic microwave background. So after it's discovered, lots to study, and the way to do it is to try to get away from the atmosphere. So even though it was discovered at sea level in New Jersey, the thing to do is to get above the atmosphere, put your telescope on a satellite, put it up in a balloon, a very high altitude balloon, or find a location on Earth that's very high altitude, dry. That's kind of my approach, right? The project I'm working on is in a high altitude desert. So okay, so a little bit more about the CMB. So the best measurements of the temperature of the CMB, the absolute temperature of the CMB, come from a satellite that was launched by NASA in 1989 called COBE, Cosmic Background Explorer. And so the first remarkable thing about the CMB is it's a very uniform thermal radiation. So here's the data. The dots are the data, and the curve is the theoretical spectrum for black body radiation at 2.725 degrees Kelvin, and you see the theory fits the measurements, perfectly. And so the first thing to say about the CMB, very uniform, characterized by a single temperature. If you have a black body, it will emit over a range of frequencies, but just saying this is the temperature, that tells you the entire curve, and that's what's observed. And by the way, this is the same basic technology that's used when you go and have your temperature measured with one of these IR devices. That's what they're doing. They're measuring your temperature with this IR. So that's the first thing. One temperature, very uniform, but a little bit of non-uniformity. So COBE measures very small non-uniformity. This is a map of the sky, right? This will be what the map of the Earth would look like in this projection. This is a map of the entire sky, and you see there are hot spots and cold spots, but these are tiny hot spots and cold spots. They're varying by 1 part in 100,000. But this is very important because these hot spots and cold spots, they encode the strength of gravity that allowed structure to form. It basically allowed our galaxies to form, allowed us to form. Okay? So there have been 3 big satellites that have flown to measure how uniform the cosmic microwave background is. The second one is another NASA satellite, and this one a European satellite, always with higher resolution, and always confirming the previous results with higher and higher resolution. So in fact, here is the map produced by the next NASA experiment called the Wilkinson Microwave Anisotropy Probe, and then here is the map produced by the European Planck satellite, and you see, there's an excellent agreement just with higher resolution here, and to just think about it, that the hot and cold spots are varying by 0.003 degrees Kelvin, right? So that's the next decimal place beyond that average temperature. Very uniform, but these very important small anisotropies. And so, this map encodes a phenomenal amount of data. So how do you analyze this? Well, one way to analyze it is by making the so-called power spectrum. So this is angular scale. So if you looked out at the ocean and you saw waves and ripples in the ocean, you look on very long angular scales, the ocean is maybe flat, and then maybe on smaller angular scales you see little white caps and things like that. And so you differentiate where's the activity on what angular scales. And so the most activity is on these small angular scales around a degree, and then there are other activity on these other angular scales. But the standard model of cosmology makes predictions for what this should look like, and by fitting a few parameters in the standard model of cosmology, in this mathematical model, you first of all, it fits the data very well. And just to point out again that ordinary matter, it includes information about the composition of ordinary matter, and dark energy. And amazingly, ordinary matter is only 5% of the universe. So the kind of stuff we're made of, the kind of stuff we see on Earth, is only 5%, 25% dark matter, and 70% dark energy. All right, so that's the whirlwind tour of cosmology. So I'll just conclude by telling you a little bit about the Simons Observatory. So the Simons Observatory, as you might guess, is looking to study the cosmic ray background just a little bit more. And, one more concept I'll introduce is this concept of cosmic inflation. So the standard model of cosmology explains things very well. We don't know enough to extrapolate all the way back to time t equals 0, but there is a proposal for something that happened in the universe very early in the universe called a very rapid expansion of the universe. And one of the predictions from this theory is that there would be so-called primordial gravitational waves, and that phenomenon would leave an imprint in the polarization of the cosmic microwave background. So light is polarized, and we would see differences in the polarization depending on where we look. In fact, it would leave a swirly pattern in the CMB. So just an example here, these lines are showing polarization, and there would be characteristic signatures of polarization. That's what we're looking for. So, science is done by people. Here's a group picture of people working on the project, from many different institutions. A meeting we had in San Diego, summer of 22. We're privately funded by the Simons Foundation. There's a picture of Jim Simons and his wife, Marilyn Simons. Hedge fund manager, billionaire. So that's where we have our funding. And the observatory is located in northern Chile. So I'll just kind of orient you. We fly into Santiago. Then we take a local flight from Santiago to Calama in the north, where there's a lot of activity mining. And then we drive from Calama about an hour to a town called San Pedro de Atacama. And San Pedro looks like this. It's kind of a quaint, adobe architecture, dirt roads in Calama. But it's a little bit of a tourist place because people come out to see the Atacama Desert. There are actually flamingos not very far away. I haven't had a chance to see them yet, my trip there. But this is a picture I took of the viscacha. Unfortunately, it's an animal that has bunny ears and also a tail like a squirrel. So this picture, you can't see it, but it's, and very large cacti. And this is a volcano just outside of town, kind of beautiful. One of the taller peaks just outside of town. And then from San Pedro, we drive. So we spend our nights in San Pedro, which is an elevation of 8,000 feet, and then we drive an hour to the site outside of San Pedro, which is at an elevation of 17,000 feet. So it wouldn't be it's not very comfortable to actually be there. It's certainly not comfortable to sleep there. So you have to sleep at lower elevation, and you drive for about 50 kilometers down the highway, and then turn off the highway and take this dirt road up the mountain. I just got these pictures off of Google. And then we come up to our observatory site. And things are looking like this. And here's actually a picture taken toward the end of last year of our site. So we have 4 telescopes, the large telescope still being assembled there, and 3 smaller telescopes that are inside these ground shields that are shown here.
That's at 17,000 feet?
This is at 17,000 feet.
13,000 feet is Colorado.
Yeah. So so I'll show you a picture of me standing there at 17,000 feet. So the atmosphere there is about roughly half of what it is at sea level. So I think I pulled it down off my nose, but I'm wearing like an oxygen concentrator. We all wear oxygen concentrators while we're there, if only to avoid a headache. But we all do it now. It's sort of our procedure. But I've heard stories of my colleagues have been working there for years, and in the good old days, nobody wore oxygen, and they all have these stories about like not being able to make good decisions, not being able to find things because So all right, so let me conclude here. I see it's been just about 45 minutes, like I hope. So we're just getting underway. We're installing our equipment. So kind of stay tuned to when the results might come. But there's a whole suite of topics in astrophysics that we aim to address. Well, thanks.
That spot for an astronomer.
So, for these kind of observations, there are really there are two locations which are considered to be the best. This one in Chile and at the South Pole, right? And so there are actually other observatories at the South Pole that are doing similar things. So there are, besides, flying things up in a balloon or having a space telescope. So there are trade-offs. With a space telescope, you've got to get things ready for your rocket launch, and there are strict limitations about how fast you can get it ready and so forth, and very expensive. Balloons are also useful, but for a finite amount of time. Usually what you do is you go to Antarctica, you go to a base, McMurdo Base, which is on the edge of Antarctica, and you do this in the summer, and you launch your balloon, say in middle of December, and the prevailing winds are such that they sort of circle Antarctica, and the balloon goes up, it's up in the air for say 20 days or so forth. It sort of circles around and then falls back down, and you can retrieve your telescope, but that's a limited amount of time. Chile it's remote, but you can buy a commercial airline ticket, and roughly in a day, you can make that journey I just described and be there. Antarctica, the South Pole, is a little bit more of a to-do, but I have colleagues who work there too, and the National Science Foundation has a base, but it's and so another thing about Antarctica is it's at the bottom of the Earth, so your telescope is pretty much pointed always at the same southern pole of the sky. Where we are, the Earth is moving around, so both of them have their advantages and disadvantages, but it's just so slightly different observations.
Yep. It's hard to get my head around 99% of what you said, so my question is probably going to be very ignorant, but I'll try anyway. Is it fair to say that the origins of the universe, the Big Bang, was an explosive-like event that set everything in motion? Is it true, therefore, to say that this constantly expanding and accelerating universe is being driven by the same energy that was generated at that time, or is it generating additional sources of energy?
So, so the idea is that early on, the expansion. So there are different constituents of the universe: radiation, matter, dark energy. And so early in the universe, so whatever dominates, they all contribute, but they'll dominate in different epochs. So at the very beginning, it was radiation that dominated the expansion. Then it changed to matter, and matter dominated the expansion for a very long time. And over the last, I think it's about 4 billion years, the dark energy is dominating the expansion. So yeah, I think for the first 50,000 years, it was the radiation that was dominant. Now, the radiation is the energy density from the radiation is so small, it doesn't contribute much at all. But so that's the way it works.
So it continues to be driven by something that originated.
Yeah. So now, what's dominating the expansion is the dark energy. But at the very beginning, the thing that mattered the most was the radiation density.
Those balloons that you said that circle around the Earth, are they remotely controlled?
So,
how does that work?
Yeah, they just get launched, and they follow whatever pattern the winds take them. So you think about Antarctica. So Antarctica's a continent, and you go to the edge of Antarctica, and it's a high altitude balloon. It goes up, and at that time of year in the summer, the winds circle around the South Pole, just around Antarctica, and so they have a chance to come around and then either fall on their own or get released. But you fill them with helium, and at some point the helium will run out, and they'll naturally fall on their own. Yep.
Why is the shape of the universe always depicted as that funnel?
Yeah. Well, that's a depiction. Yeah. So right, you see it here, and you know, I would say, so what does it really mean? So, you know, there's something here, and then it expands very quickly. And so when I mentioned that cosmic inflation, that would be that, you know, a depiction of this very rapid expansion. And then things expand, you know, all of the very hot activity, the activity that forms, you know, hydrogen and helium, that's all explained by the standard model of cosmology. So, you know, it's one of the triumphs that you can explain the abundance of these light elements by what's going on, and then you explain this plasma, the cosmic microwave background. But yeah, and then at that point, you know, it's expanding in a sphere, but this is, you know, they just want to, you know, need to depict it somehow, this funnel. And this is kind of the depiction of what I had, where you say, you look out, you see the most mature galaxies here, the less mature galaxies here, and then, you know, and then this dark area here before the galaxies had a chance to form.
So within that funnel, if you look back in time, right, towards the early universe, and you know that things are expanding at an increasing pace, is the movement of galaxies in that tunnel predictable? Is it do they follow, you know, some common vectors? I've always wondered if you can look back 13 billion years now and see that, what makes us sure when we're looking back that far that we're not looking at similar objects across time? Does that make sense?
Oh yeah, so your one question is, how do we know we're looking at something really far away and not...
And that's unique and not another picture of itself a billion years later in a slightly different position in the universe.
All right.
That's always bothered me. I'm sure it's written about somewhere, but I don't understand it.
Okay, there was something else I was going to, in the early part of your question was, about how they're moving.
Right.
You know, so, well, one thing I was going to say is, you know, so when we see the cosmic microwave background, we see hot spots and cold spots, and I guess you would say, well, okay, if the fact that we're here, the fact that our local group exists as a you know, an entity, means that there must have been something imprinted in as the fluctuations from the Big Bang that caused you know, gravity to clump. And so in this kind of mind experiment, if you could switch places and be in a place where you were looking at the CMB to where we are, presumably you would see some imprint of that, you know, is what caused gravity to form and have us here. So that's, you know, it's a, you know, not exactly what you're saying, but it's, you know, it says that somehow, you know, from the very early universe, the way the fluctuations were in hot spots and cold spots, you know, that's what made gravity clump in different places. That's what made galaxies form in different places. I haven't heard of, you know, trying, because there are maps of observations of galaxies, really mapping out the galaxies in the universe. And you were talking about, like, can we predict the trajectories of things? I don't know a lot about that, but I think it, to some extent, yes. I mean, I think things are being measured, and then, you know, you can look at their velocities and then try to map out, you know, where things were, where things are going, you know, what might happen.
But everything observable
is unique. Is that in terms of galaxies, they have a signature, right? If we can
say that's.
Yeah, so these, you know, these maps of galaxies are extensive, and they, you know, literally making 3D maps of objects around. Yeah, and then, you know, I probably don't know the details, but these kinds of questions, I mean, how do we know we're not just fooling ourselves by
by seeing something up close that we think is far away, how do we know things are extragalactic? I think these kinds of questions, these are what cosmologists ask themselves, say, well, how do we know that? How do we know we're not being fooled? Yeah, those are important.
I have a question. You said that initially this started with the energy, then it turned into black matter because the energy got weaker. Is there a theory that eventually all of this is going to end?
So that's the thing, so right now, the expansion of the universe, the component that's most important is the dark energy. And so the amazing thing is, before people were thinking, well, what will happen? Will things keep on expanding? And then now the energy densities are so low that gravity will start to suck everything back together, and there'll be a compression and a big crunch. But instead, because now we think that space itself has this pressure, this cosmological constant, this dark energy, that's where the evolution is going to take us. So the thinking is, because this is a fundamental property of space, it's going to keep making things expand, and that's the fate of the universe, keeping on expanding.
How about that?
It will end in when you say, will it end in fire, will it end in ice, looks like ice.
Yeah, in the back.
Does this expansion have any impact on climate change?
So no, this is it's just that it's the dark energy, dark matter, the expansion of the universe doesn't really impact what we do here on Earth, right? This is something to think about looking out into the universe. But you say, well, the universe is expanding, space is expanding. Does that mean I'm expanding? Well, in a different way. But in fact, is the distance from the Earth to the Moon expanding? Is the distance from the Earth to the Sun expanding? The answer is no. Though the forces, those gravitational forces are stronger than they keep things where they are, and space is expanding kind of underneath them. It's only on these cosmological scales that the galaxies are expanding, moving away from each other.
I guess sort of since we're in a St. Sophia religious society, let me ask you a question. And that is that our basic human instincts tell us that everything must have a beginning, it must have an end, it must have an edge.
Right.
I'm not saying that we know this.
Right.
And also, energy has to be released, and then it gets exhausted. You kind of said that we know that there must be, or we perceive an edge to the universe, and we know that it must exist, and yet we can't wrap our heads around it, as far as I can tell. So in this process, for all these inferences, do you think that we're ever going to be able to perceive and understand those concepts of beginning, end, exhaustion of energy, introduction of energy?
Well, I think I think I described kind of how we know things now. So, when we talk about the age of the universe.
And I get you have to assume certain things
to
do science.
You observe things now, you extrapolate them back. The point is they extrapolate back to one place, one place. What do we know about that? Was there something before that? Maybe. But then we can't really say that right now. So, and there are theories that are cyclic. That maybe this Big Bang is just in a cycle of, say, other Big Bangs. So it could be, right? And I talk about the observable universe. What's beyond that? We don't know. Maybe we can never know. So these are big questions.
Just a comment. Somehow your talk makes us feel very insignificant.
Well, so I think there are kind of two reactions.
There are two reactions. I think one is to think that we're not the center of the universe. right? But another way to say, wow, you know, the universe is so vast, there's so many possibilities. So, you know, maybe I choose to think of it that way.